Alright, let's start with the geometry of the rolling wheel. Let's assume that the wheel is rotating in the clockwise direction and every point on the rim of the wheel has a velocity v. Assume that the center of the wheel is the point O, the radius is r. Draw an imaginary horizontal line through O that will cut the rim of the wheel at A. Similarly, a vertical line through O will cut the rim of the wheel at the top at the point B. It is at the point C in between A and B on the rim of the wheel that a mud particle, will fly off the wheel. Join O to C and let's assume that the line OC makes an angle alpha with the horizontal. Now point A is at a height r above the ground, and from simple trigonometry we can deduce that the point C is at a vertical height of r sine alpha above the point A. Now the mud particle will take off tangentially at the point C with a velocity v. If we were to draw a vertical line through the point C, the angle between this vertical line and the tangent v is equal to alpha, because two lines perpendicular to these two lines, namely the radius OC and the horizontal OA, is also equal to r. Therefore, the vertical component of the velocity v is v cos alpha. Now this alpha is where our adventure starts. For some value of alpha, the total height attained by the mud particle is maximum. The question is, what is that alpha and how do we find it? Now we can think of this problem in simple terms, relating to the vertical movement of the mud splash. We are not really concerned with the horizontal component of v because we don't really care how far horizontally the splash will go. The rider of this carriage is at risk only if the mud splash travels sufficiently in the vertical direction. So, if the object, in this case the mud splash, starts moving vertically with a velocity v cos alpha, after a height say h, which is the maximum vertical height it will attain, the final velocity is 0. From simple equations of motion, we can say that the final velocity 0 is equal to the initial velocity v cos alpha plus acceleration, which in this case is minus the gravity g, because we are moving against gravity, times the time taken to reach this maximum height h. Let's denote it by capital T. Therefore, T is equal to v cos alpha upon g. Next, we ask ourselves, what is this height h, which is a function of alpha, that this particle will reach? This is equal to the initial velocity v cos alpha times the time capital T plus half of acceleration, again this is minus g, times t square. Now to find the maximum height h alpha, we plug in the value of t determined above. Therefore, h of alpha is equal to v cos alpha times v cos alpha upon g minus g upon 2 times v square cos square alpha upon g square. In the second term, g cancels across the numerator and the denominator, and we get v square cos square alpha upon g minus half of v square cos square alpha upon g. The second term is merely half of the first term. Therefore, h of alpha is equal to half of v square cos square alpha upon g. Now note that this height h of alpha is the height achieved after the mud splash takes off vertically from the point C. Therefore, h of alpha is the vertical height above the point C. Now the height of C above ground is equal to the height of C above A plus the height of A above ground. The first term we have learnt earlier is r sine alpha, and the second term is equal to r. Therefore, the total height of the mud particle, let's denote it by h subscript t alpha, is equal to r plus r sine alpha plus the height attained by the mud particle above the point C, which is half of v square cos square alpha upon g. Now this is what we have to maximize. Derivative with respect to alpha of ht alpha is equal to 0. We take the derivative of the above expression, we get r cos alpha plus v square upon 2g times the derivative of cos square alpha, which using chain rule is equal to 2 cos alpha times the derivative of cos alpha, which is minus sine alpha. And we set this equal to 0. On the left hand side, in the second term, 2 cancels across the numerator and the denominator. And this expression simplifies to r cos alpha is equal to v square upon g times sine alpha cos alpha, which implies that sine alpha is equal to rg divided by v square. Now recall that the absolute value of sine of an angle is always less than or equal to 1. Therefore, in this case, rg upon v square must be less than or equal to 1, which implies that v square must be greater than or equal to rg. So this becomes our first case, which is when the square of the velocity v square is greater than or equal to rg. Let's examine this further. Again, remember that ht alpha is equal to r plus r sine alpha plus v square cos square alpha upon 2g. Substituting the value of sine alpha derived above for maximum height, ht alpha, let's denote it by capital H, is equal to r plus r times rg upon v square plus v square upon 2g times cos square alpha, which is equal to 1 minus sine square alpha. Substituting the value of sine square alpha is equal to r square g square upon v raised to the power 4. This is equal to r plus r square g upon v square plus v square upon 2g minus r square g divided by 2v square. The fourth term is half of the second term. We combine them and therefore we get capital H is equal to r plus r square g upon 2v square plus v square upon 2g. Now note that this expression depends on the value of v square. which is present in the second and the third terms of this expression. Of course, the other terms, r and g, are merely constants. In the second term, as v increases, the value of the second term decreases, and in the third term, as v increases, the value of that term increases. So at what value of v square does this expression become maximized? To figure that out, let's make some simplifications. Let's denote r squared g upon 2 by a in the second term, and in the third term, 1 by 2g by capital B. And let's denote v square by u. Therefore, the second and the third term combined become a upon u plus b times u. This is a function of u. Let's denote it by f of u. To determine its maximum or minimum value, we take the first derivative. This is equal to minus a upon u square plus b. And if we set this equal to 0, we get u square is equal to a upon b. Substituting the value of a and b in the numerator and the denominator, we get r squared g upon 2 divided by 1 upon 2g. And this is equal to r square g square. Therefore, u, which is equal to v square, is equal to rg, which means that v is equal to the square root of rg. Again, take the derivative of f dash u, we get f double dash u is equal to plus 2a upon u cube. Because both a and u are positive, this expression is positive, and therefore f of u achieves a minimum at u is equal to rg, and its value is equal to the value of a upon u plus b times u when u is equal to rg. Substituting the value of a, b, and u, we get r squared g upon 2 divided by rg plus 1 upon 2g times rg. Both terms simplify, and therefore the minimum value of f of u is equal to r upon 2 plus r upon 2, which is equal to r. Therefore, capital H achieves its minimum value when f of u achieves its minimum value is equal to r plus minimum value of f of u which is equal to r plus r, which is equal to 2r. Therefore, the value of capital H will always be greater than equal to 2r. And this is true when v square is greater than equal to rg. What does this mean in the physical sense? We come back to the figure. The wheel with radius r on the ground the center is at a height capital R above the ground, and the top of the wheel is a further capital R above the center. Therefore, the total height of the top of the wheel above the ground is 2r, which means that the mud splash will rise a distance of capital H above the ground, which is greater than equal to 2r, which means that the mud splash will rise above the wheel, meaning a height more than 2r above the ground when v square is greater than equal to rg. Now, there is nothing stopping the velocity from being less than the above threshold. So that becomes our second case. What happens when v square is less than rg? Again, ht alpha, which we have derived earlier to be equal to r plus r sine alpha plus v square cos square alpha upon 2g can be rewritten as r times in brackets 1 plus sine alpha plus v square upon 2rg multiplied by cos square alpha. Now, in the third term, v square is less than rg in this case. Therefore, this whole expression is less than r times in brackets 1 plus sine alpha plus rg upon 2rg multiplied by cos square alpha. In the third term, rg cancels across the numerator and the denominator. Therefore, ht alpha is less than r times in brackets 1 plus sine alpha plus half of cos square alpha. Now, this term inside the square brackets is a function of alpha. Let's denote it by g of alpha, and let's examine when it achieves its maximum or minimum. Take the derivative of g with respect to alpha. We get cos alpha from the second term plus from the third term half of derivative of cos square alpha, which is equal to 2 cos alpha times minus sine alpha. And this is equal to cos alpha times in brackets 1 minus sine alpha. Now, sine alpha is always less than or equal to 1 for all values of alpha. Therefore, 1 minus sine alpha is always greater than or equal to 0. And the first term outside the brackets cos alpha is strictly positive for values of alpha lying between 0 and 90 degrees, which is the case here for the rotating wheel. Therefore, the product of both these terms will be strictly positive, which means that the function g of alpha is an increasing function. As alpha increases, the value of g of alpha also increases when alpha lies between 0 and 90 degrees. Therefore, the maximum value of g of alpha is reached when the value of alpha is maximum in this range, which is equal to the value of g when alpha is equal to 90 degrees, which is equal to the value of 1 plus sine alpha plus half of cos square alpha when alpha is equal to 90 degrees. And this is equal to 1 plus sine of 90 degrees plus half of cos square 90 degrees. And this is equal to 2. Now, we had determined earlier that ht alpha is less than r times in brackets 1 plus sine alpha plus half of cos square alpha. And that expression in the square brackets, which is g of alpha, achieves a maximum value of 2 when alpha is 90 degrees. Therefore, this whole expression, ht alpha, is less than 2r. Therefore, when v square is less than rg, the maximum value of ht alpha is equal to 2r. Again, in physical terms, what this means is that you have a wheel on the horizontal ground. The top of the wheel is at a height of 2r above the ground. And so it means that the mud splash will stay below the wheel when v square is less than rg. And this gives us the answer for the maximum speed of the carriage so that it can avoid splashing the mud above the wheel. This V max is equal to the square root of Rg. So, if the radius of the carriage is equal to 1 meters and gravity is equal to 9.8 meters per second square, we get V max equal to the square root of 9.8, which is equal to 3.1 meters per second. To convert this into kilometers per hour, we divide by 1000 and multiply it by 3600 seconds in an hour, and we get 11.3 kilometers per hour. And so the carriage should stay under a speed of 11.3 kilometers per hour. It's a gentle trot, but it will keep Cinderella's dress safe. Small price to pay. After all, she is destined to be the princess of the land.